companies, when they're planning to build data centers in the future, they're planning to build power plants. Some are investing in nuclear energy because these data centers in the future are going to consume like over a gigawatt of power, will run out of electricity. Now, if the chips could be more energy efficient, then they wouldn't generate as much heat. Not only do you consume less power to do the computation, but you eliminate the need for air conditioning. So it's a tremendous advantage. You have to start with some niche market where you have a real competitive advantage. Eventually, you can become the dominant technology. This is kind of what we're aiming for, is to facilitate more disruptive innovations.
We're shrinking down the density of microelectronics into a spot where there's no longer the laws of physics that allow for the shrinking to happen. Where do you see the future of innovation in hardware for microelectronics? Hey, Tsu-Jae, thanks a bunch for joining us here on MicroJourneys. Pleasure to have you here on the podcast.
It's a pleasure to be here. Thank you, Daniel.
Fellow California native, it's nice to have the opportunity to sit down and chat, and very curious to understand a little bit of your background and go through your illustrious career in electronics, microelectronics, and a variety of other different areas. I think it all started over at Stanford, correct?
Yes, in terms of my higher education, that's true. I grew up in the San Francisco Bay Area in a town close by to Stanford. So it was not very imaginative of me to major in electrical engineering, having grown up near Silicon Valley in the heyday, and just going to Stanford. It was a safe bet from my perspective. I knew it was a good school.
Well, did you have a passion for electronics early on, or what drove you in that direction?
Well, early on, I was still wondering perhaps if medicine was a field for me. So I did have a chance to take a field trip to the Stanford Medical School, and I visited the anatomy lab. This actually happened when I was still in high school, and I really couldn't stomach all the cadavers and the body parts, and I decided it's probably not so good for me to become a doctor. But I knew that doctors used equipment, things that are designed by electrical engineers to diagnose and treat patients. So I thought engineering would be a good field, alternative field for me to pursue.
Now, when you got into electronics or engineering, was your goal to go all the way through your PhD, or was this something that happened over a course of time?
It certainly happened over a course of time. I did not plan in advance. I was just hoping to get a good job after I graduated from the university. But I felt that I wasn't well prepared enough to excel as an engineer when I was getting close to finishing my bachelor's degree. And at Stanford at that time, it was relatively easy to stay for an extra year, a fifth year, to earn a coterminal master's degree. And so I took that option to get more in-depth training in electrical engineering. But to help support myself, I served as a teaching assistant, and I realized I really enjoyed teaching. And I also got to know a lot of graduate students who were pursuing their PhDs, including today my husband. And it really intrigued me that seemed like they were really enjoying the research. And so I thought, maybe I should try the PhD program too. So it's more like I didn't really know what I was doing, and I enjoyed school. And I enjoyed learning, so I just happened to stay on. And fortunately, Stanford allowed me to continue after passing the PhD qualifying exam there.
Now, electrical engineering is a very broad, topic. How did you narrow it down, and what was your focus for your PhD?
So it was interesting. I was very much influenced by the people I hung out with. So as I mentioned, my husband, he actually was the one who chose to specialize in semiconductors. And so I learned about this through the field through him. And it looked really fun. Got to work in a lab. I guess I just happened to luck out that it was a good field to enter into. I have a lot to thank my husband for. So it's more like stumbling. I did not plan in advance that I knew that semiconductors would have tremendous impact in the world. And so that it would be a good field for me to go into research. But I knew I enjoyed learning. I enjoyed the material. I enjoyed working in the lab, teaching students how to work in the lab. So I was fortunate that it all worked out for me in the end.
And I mean, what a great decision in the overall course of time with microelectronics and semiconductors being a foundational technology. all other technologies require them. One of the examples I like to use is you can't have hypersonics without microelectronics, but you can have microelectronics without hypersonics. So
First time I heard that,
yes,
but it's true.
so it's a great foundational piece, which led you to, I would say, the next portion of your career over at Xerox, correct?
That's right. So Xerox has a Palo Alto Research Center, Xerox PARC. I had the privilege of working there because I enjoyed teaching. So I thought it would be good for me to work in a industrial research lab so that I could continue to do research and publish, and also help to supervise graduate students in research because I knew that that experience would be helpful if I ever wanted to become a professor. So at the Xerox Palo Alto Research Center, I worked on semiconductor devices and process technology as well. And at that time, the information displays were still primarily these large cathode ray tubes. I don't know if you have seen them in a museum, but they're pretty large and bulky. So displays like what you see here in our background, or your phones and on your laptop computers, those flat panel displays were not effective to manufacture yet. And those displays each use at least one transistor formed on the surface of glass substrate that's used for the display to control the brightness of and the color of each picture element in a display, each pixel. So today, the most modern high-end information displays have many millions of pixels and therefore many millions of transistors on a piece of glass, and they have to all work in a uniform manner and be low cost to fabricate. So at Xerox PARC, I was involved in research to develop the thin film transistor technology that would be used to drive these flat panel displays.
Very interesting. There was also a portion of your research there, I believe, that helped to influence FinFETs, correct?
Maybe a little bit. So one of the challenges for making thin film transistors cost effective is that they should not require very high temperatures to form because glass doesn't have a very high tolerance for heat. So I gained more expertise in thin film technology that was compatible with lower process temperatures. And it turns out that that was an advantage. That technology was also useful for advancing the state of the art in transistors that are used on microchips for computing applications.
Interesting. You referenced a couple times your interest and passion in teaching, or kind of integrating in with students and the such. And there was, I believe, another portion of your career where you went back to academia into UC Berkeley, correct?
That's right. I had the amazing opportunity to join the faculty at UC Berkeley, kind of a rival, football rival to Stanford, but it's really welcoming and supportive colleagues there. The students are outstanding, highly motivated, and I really have been blessed to work with outstanding colleagues at Berkeley for almost 30 years.
Well, and it's timely you mentioned the football rivalry. Right now, while we're filming this, the NCAA season is about to start. So the sky's the limit for many of these institutions to see how their football programs go. But while at Berkeley, you covered a wide range of things, everything from being the dean to overseeing the College of Electrical Engineering. I mean, describe how your progression went through there, and some of the,
Hmm.
I guess, memorable moments that you've had as you've been associated with UC Berkeley.
Well, I certainly remember being taught by my students. I remember teaching initially the first courses I taught. I didn't get very high teaching effectiveness scores, and I was trying to figure out how to improve. And the students there taught me a lot. But that was the first time I realized, oh, different people have different ways of learning. So, like the instructor needs to be aware and adapt their teaching to different styles of learning. So that was one thing I learned about learning in general. But you never learn a material as well as when you're actually required to teach it. So I think the fact that I was able to teach a variety of courses helped me learn the material well, and that made me a better, more effective as a researcher and a mentor for students. So teaching was definitely something I loved and I really enjoyed at Berkeley. And then in terms of research, we got to work in large research teams at Berkeley, which is not back then 20, 30 years ago, that was not as common. Today, it is common to have large research teams working together to solve multidisciplinary problems. But back then, it was more common to have like a single graduate student working with a single professor on a project and writing their thesis. But at Berkeley, they have a strong tradition of collaboration. So I got to work with more senior faculty and their students and postdocs. We've got to work with visiting industrial fellows, and that was a really rich environment for brainstorming ideas of solutions to problems that the semiconductor industry was facing at the time. So really enjoyable team experience. I really enjoy working in teams.
Yeah, kind of circling back to the reference of FinFET, UC Berkeley has had such a major influence in that
Mm.
particular, technology focus area. I mean, names like Chiming Hu, for example, were influential in some of the development early stages of those technologies. So, I mean, to kind of quantify how impactful that university has been. I mean, it goes in tandem with your leadership as you were there. So, was there any particular, I guess, technological milestone that you were able to either oversee or experience while you were over at UC Berkeley that really stands out to you?
Well, first demonstrations of the FinFETs, so fin-shaped transistors, were certainly a major milestone. Back then, the state of the art manufacturing of semiconductor chips was quarter micron minimum feature size. So that's 250 nanometers. And the Defense Advanced Research Project Agency had a program to investigate, okay, what kind of a miniature switch can be scaled down to be 10 times smaller, to be 25 nanometers in minimum dimensions. And so we had to demonstrate that our approach, the FinFET, in the end, it was dubbed the FinFET, could actually meet that requirement. And in fact, we eventually showed that it could be scaled down to 10 nanometer minimum feature size. And that was very rewarding. It was a team effort. My student was the first student to publish a paper on the FinFETs in 1999. So that was very rewarding. And looking back, I think um, one person more recently pointed out to me, hey, if you think about the number of FinFETs that have been manufactured in the world to date, starting in 2011, when Intel first introduced it into their leading edge computer chips. So it's been almost 15 years. And today there are billions of transistors, FinFETs on microchips, GPUs, CPUs, XPUs, NPUs. Um, the number of FinFETs that have been produced over these years, numbers greater than the number of grains of sand on Earth.
Whoa,
Yeah,
interesting.
an
Um,
interesting factoid.
Yeah, I mean, it really kind of helps to quantify all the different, applications that we have that we leverage for electronics to have that amount of FinFETs that are fabricated, and that's the state of the art, right?
Mhm.
So this is something that really shows that there is a huge demand in this space that's powering a lot of things that we leverage today. Everything from the uptick in AI that people are looking at to some of the capabilities that NVIDIA has, for example. I mean, it's not only been an influence, but is now become part of our daily lives, which is really, really interesting.
Yeah.
And for those that aren't familiar with the FinFET, and tell me if I get this right, we were losing space on the XY axis or the planar axis. So the decision was to see how we could go vertically with our transistors. Is that a correct
Well,
statement?
in the end, that turned out to be one advantage of the FinFET structure. So, um, if you take a chip, it's cut from a single crystalline wafer of silicon, and so the transistors are traditionally were fabricated on the surface of the silicon. So let's say this is the surface of the silicon, and you put a gating electrode here. To the voltage the electric potential you apply to the gate controls whether or not current can flow uh, across the silicon surface. And the width of that gate, that's what was becoming difficult to scale down to be less than a quarter micron. So it's kind of like, so my colleague Chen Ming, who explained it this way, that's the purpose of the gate is to turn on and off the electric current flow in the semiconductor. So let's say you're trying to pinch off a hose with water flowing through it. So you can push down from one side to shut off the current flow, or you could try to squeeze it from both sides and better control the current flow. So that was the concept that was already known in the field, that if you have a gate on both sides of the semiconductor channel for flow, you can actually get better control. So then this dimension can get smaller. But the question is, how do you manufacture a transistor where the gate electrode on the bottom is perfectly aligned with the gate electrode on the top? And it turns out that the FinFET achieves that by turning the silicon on its edge. So if you make the silicon a fin, then the gate electrode wrapping on both sides, it's, if you look top down, it's just a straight line. So it's just easy to pattern a straight electrode over that runs up and over the fin. That it's just turned out that that is the easiest way to manufacture this so-called double gate transistor. And then the taller you make the fin, the more channel area you have to conduct current. So you can actually conduct more current in a transistor by making the fins taller, and that saves area, so you can fit even more transistors per unit area on a chip. So it just turned out that the FinFET helped to also improve the density of current flow that's being controlled by all the voltage signals on the chip.
And now you can compress even more
Mhm.
the area between that fin,
Right.
right?
So the footprint, so the how much space on a chip the transistor takes, it can be scaled down because the gate width could, or we call it the gate length, could be scaled down. But then you can also make the semiconductor taller so that you don't need as much. Otherwise, you would have had to make the silicon wider like this, and that takes up more footprint. But if you make it a taller fin, it doesn't take up more footprint.
Which
Right.
goes to the reason why there's more FinFETs than grains of sand because of the area now shrinking down, right? And being able
Well,
to
so
be
so you,
compressed.
yeah, so you can fit more transistors on a chip, 100 billion transistors on a chip, the size of your palm, and then you have lots of billions of hundreds of billions of chips being manufactured every year for data centers, for your cell phones, for your displays, display drivers, for Internet of Things. You know, you have smart homes, smart factories today, smart cars. They all have chips. I mean, the most advanced vehicles have many thousands of chips controlling everything, um, every function of the car.
And I would say that this was a monumental discovery within the semiconductor industry. I mean, there's only been a few, points in time where the entire industry was revolutionized by a concept that actually turned into something that went from an academic experience into something that is now going into industry. Is that a true statement?
Well, perhaps in terms of hardware, there certainly have been innovations in circuit architecture, computer chip architecture, and in data, like data management, like database architectures. So depending on what layer of abstraction you're talking about. But in terms of semiconductor devices, yes, it is true. It has had a revolutionary impact. Turns out that if you can increase the number of transistors on a chip, you increase the functionality for that similar cost, ideally, cost per function. And so this has made it possible to have greater computational ability at affordable cost. And so if you look back, every 10 times increase in density, transistor density on a chip, has enabled a new class of computers to become commercially viable. So you go from like a mainframe computer to a personal computer to mobile, and then cloud. And today it's like sky.
Yeah.
Yes. So it has had tremendous impact. And with each new class of computers, you have greater computational ability. And with the proliferation of chips, because you make these chips more affordable, you collect more data, right? Cars today collect so much more data. So if you have lots of data and you have the ability to compute on that data, process it more quickly in real time, this is what has enabled the AI revolution, because you need lots of data and you need computation for real time decision making.
Interesting. One of the things that you mentioned in the description of the work at UC Berkeley is the company Intel, and you're one of the few academic experts that has been able to bridge the gap between academia and industry. And one of the things that is extremely interesting, at least from my perspective, was the influence that you had at Intel Corporation. Would you mind describing that a little bit about how your role there?
Not sure. of what kind of influence you're referring to, but certainly Intel through the Semiconductor Research Corporation did sponsor some of the research on FinFET. So after the DARPA funding ended, that project ended, the industry still wanted to know, okay, you can make transistors really small, but how reliable are they? And how well can you control their characteristics? Can you make every transistor turn on at the same voltage? Or do you have to, like, how reliable are these devices? So the industry, including Intel, did fund research to show that indeed it's scalable and you can stress these transistors. They're if you design them properly, they can be just as reliable as the state of the art planar transistors. Um, and one of the so I talked about materials innovation, like the work I did at Xerox PARC, that turned out to be useful because you needed advanced materials to be able to design the FinFET to operate with the right range of voltages. So that was not a trivial challenge to overcome. But my work in the past, including as a PhD student at Xerox PARC, did help to innovate some technologies that were critical to enabling the FinFET to become a commercial success.
And outside of the research angle, I believe you held a board of directors.
Or in recent years, yes,
Yes.
and I recently concluded that service. And that gave me insight into the business aspect of semiconductors, which I have to say I didn't fully appreciate in the past. Um, and so I think that influenced me to think about how we educate future engineering leaders today. So as an educator, it's important for the students to gain knowledge and skills that are technical, but also in addition to teamwork, communication skills, but they need to be societal, socially aware, but also like aware of like business aspects, financial aspects, because you might have the greatest new invention, but if it's never going to be practical to commercialize, then your impact is going to be limited. And engineering is all about advancing technology, making innovations that will benefit somehow people and society. And if you don't have that positive impact, then as an engineer, you're not going to be considered as successful.
Yeah, and it's interesting talking about the business aspect and how it impacts the engineers with the semiconductor industry being such a cyclical type of industry, and every single company that is either publicly traded or working in this space, quarterly earnings is a major driving function, which helps
Yes.
to either drive more engineering work to be done, or there's a variety of different impacts that it has. So being able to connect that, from all different levels, those that are doing research to those that are, like you said, looking at the business aspects of these, bridging that gap is a
It's really important. So appreciating the business aspects, especially market, right? First of all, you need to have some market advantage, and probably doesn't make sense to go into a business if you know you're going to be third or worse. You have to make money so that you can continually advance the technology and new products continually. You need to be number one or two, ideally, in your in the product category. Otherwise, it's not worthwhile. Also, some of us tend to be perfectionists, like, okay, we can do even better. So give us more time, give us another month, give us another quarter, give us another year. We can improve this technology, but then your market window has passed. So I think this is these are some aspects of having a successful technology business that I didn't fully appreciate when I was just focused on research. So serving on public boards certainly helped to expand my knowledge and appreciation for the business side of a company. That's for sure. Because I was more focused on advancing the technology to enable great things. That's not enough.
Well, it's interesting the way that you just described that. I'm picturing Gartner has something called their hype models, and it'll show when a technology is, in the laboratories and the such, and the performance characteristics of those are really, really showing a lot of benefits, right?
Mhm.
But the reality of that going from concept to actual production has a entire, spectrum of things that have to happen.
Mhm.
So, people get really excited about a technology, and then by the time it's starting to get out of the concept phase into the prototype phase, and then into the production phase, it goes through this huge cycle of stuff. So it really emphasizes the point that you just mentioned, which is that time window, right?
Right. You
There,
want to have customers adopt your technology. So what if it's not the best yet, but it's still slightly better than whatever else is out their other options are? It's good enough. You don't have to like overshoot too much. It's more important to engage and get the customers hooked. Yeah.
and that is the key point. Without a couple, you know, I'd say foundational customers, you can miss that window. And
Mhm.
it doesn't matter if you have the next node size that is just amazingly better than all others. That customer needs to adopt this, integrate it into their products at volume, which is the big kicker,
Mhm.
or else you miss the window. And then your competitors
Yeah.
take it over, right?
Right. And sometimes really good ideas, amazing innovations are before their time. So innovations, let's say in AI, that was decades ago, but it was just before the time because the computational ability wasn't like to where it needed to be, and the ability to gather enough data. So, yeah, in terms of let's say the flat panel display technology, the the reason why companies were interested were, well, let's say Xerox originally it was their biggest business. One of the a big portion of their revenue was selling paper, for the copiers, printers and copiers, and they were considering, well, maybe with the digital revolution, people are not going to need to print out things. They're going to have these displays, so we better like think ahead and work on these displays. But it took a little bit longer for those displays to be cost competitive to actually ramp up, and by that time Xerox had decided to stop working in that. I mean, not to commercialize the technologies that we developed. So they were commercialized primarily overseas.
So, we described your influence in the academic space and then serving on corporate boards. One of the areas that brought us together in for today's conversation is the influence that you've had with what I would call a transformational program that the United States is funding right now, which would be the Microelectronics Commons Program. For those that are not familiar with this, it is a subset of the CHIPS initiative, Section 9903B, which would be a $2 billion funded activity
Yes.
spread over a 5-year period with $400 million increments over each of those years. Within that, there was 8 hubs that were selected that are spread all across the United States with a varying set of technology focus areas. The one that you're leading the charge with is in Northern California, and I believe it's a collaboration between UC Berkeley and Stanford as the leads for said hub.
Yes.
So, can you describe a little bit about the hub and what the initiatives are
Sure.
over there?
My pleasure. So the California Pacific Northwest AI Hardware Hub, or Northwest AI Hardware Hub, is yeah, very focused on advancing the state of the art in AI hardware because the researchers in this hub, which include universities from the state of Washington, state of Oregon, and Hawaii. This is why we call ourselves Pacific Northwest. We recognized that if AI is to reach its full potential, then we really do need to make revolutionary advancements in the way we design the AI hardware because otherwise we'll run out of electricity. So you might have seen in the news today that companies, when they're planning to build data centers in the future, they're planning to build power plants. Some are investing in nuclear energy because yeah, these data centers in the future are going to consume like over a gigawatt of power. That's assuming that the chips today are not going to improve in terms of energy efficiency. So how do we improve the energy efficiency of AI computations uh, by a factor of 1,000? Okay. That's the goal of the Northwest AI Hardware Hub is not only we have some ideas already proven out in research labs, but the big gaps that the Microelectronics Commons Program is filling is bridging the gap between university research and like high volume production by industry. So we want to bridge that gap. We want to have some demonstrations of integrated systems that have significantly improved energy efficiency, then we can pass it along to semiconductor foundries that manufacture chips for the chip design companies like NVIDIA and so on and so forth. So it's really bridging that gap between university research and high volume production. That's something that the United States has had a challenge to fill. We see that innovations happen here, but a lot of them are scaled up or in manufacturing, high volume manufacturing overseas. And we saw that during the pandemic, um, there was a weakness. There was a chip supply chain um, missing link, and so a lot of American manufacturers didn't have access to the chips that they needed in order to complete their products and sell them. The biggest example that people refer to is the automobile industry, where just in 1 year, $200 billion of revenue was lost by the U.S. Automobile industry because they couldn't finish the cars, and so they had to sit in the lots waiting for the chips to come. So we never want to see that happen again.
Yeah, I
Um,
remember, trying to buy a car and heat, for my seat, was the big delay because they couldn't get, a 30-cent component,
yeah,
and it was, I think, a 8, 9-month delay for me to get it, and I ended up punting on said car, going with one that was already on the lot, and I says, "I don't need the heated seats." I live in Sacramento, California, it doesn't get cold enough, right? So,
yes.
anyways, I
Yeah.
interrupted you.
No, so, and that so the price of new cars went up because there were fewer of them available, and then price of used cars went up, and that did affect, inflation, right, in this country, and, there were a lot of workers in that one industry who were furloughed, so it really affected the livelihood of thousands, if not tens of thousands of people, um, and I was in one of our industry gatherings. The CEO of Ford Motor Company explained the impact on his business and the employees, and he pointed out Ford doesn't only manufacture cars like for passenger vehicles. They make trucks, they make ambulances, fire trucks. I mean, like imagine production of those being halted because of a missing link in our supply chain. So we need to rebuild the capacity in the United States to manufacture leading edge components. Otherwise, the U.S. will not stay competitive technologically for the long term.
You know, you mentioned an interesting piece. It's a little tangent to the work that's being done at the hub, but the power needed for a lot of these AI centers. One of the most recent announcements is, I believe it's Microsoft is building out a fusion capability that'll be localized near some of their large data centers to be able to create the power required for keeping up with the demand at the data centers.
Might be
There's
fission still.
maybe
Fusion is still more than a decade away, I think.
well, it it really is a testament that the power companies are not producing the types of power required for these types of data centers. Many are requiring 50 megawatts, 100 megawatts of power, for said data centers. How is the hub looking to either be influenced by these things? Are you incorporating these types of concepts? How does that play into the hub's ecosystem?
Well, maybe those companies might be interested to, well, companies that care about lowering the cost of electricity usage, because the cost of running a data center, more roughly half, it's very rough, is spent on powering the chips and actually on cooling the chips, cooling the data centers. Now, if the chips could be more energy efficient, then they wouldn't generate as much heat to begin with. So not only do you consume less power to do the computation, but you eliminate the need for air conditioning. So it's a tremendous advantage if we can fundamentally find ways to lower the energy consumption for these AI workloads. And that requires innovations not only in the algorithms that are used, but also in the circuit architecture and the transistors and so on and so forth. So it's like maybe looking at nature. Should we have completely different architectures rather than the von Neumann architecture, or maybe we should mimic nature because our brains take only a few tens of watts to operate, and they can actually perform functions pretty quickly. So our brains are actually quite energy efficient. So should we look at neuromorphic computing, where you don't really have switches that are separate from memory, like the computation is not separate from where you store the information. So it requires a lot of innovations in the architecture, in the algorithms, and the fundamental transistor technology. And we have to co-innovate and co-optimize across all those layers of technology in order to achieve our goal of improving energy efficiency by 1,000 times.
So, from a hub perspective, uh, at the end of the 5 years, what would you say would be a success? And what I mean by that is, if you were to have all of the great minds that are helping to influence with all of the different, projects that are going there, are there specific milestones that you say, if we're able to accomplish blank, this would be success?
Yeah, that's a good question. Um, well, I also forgot to mention, a lot of the power consumed in a data center is moving data not only back and forth on a chip between the storage and computational engine, but from rack to rack and across racks across a data center. And so that involves can we communicate information in the form of light, photons, bits of light, rather than moving electrons back and forth? That can be faster and more energy efficient. So I think if we can advance the technologies, the photonic interconnects that are maybe even on a chip, advanced memory devices integrated with transistors to enable compute in memory or neuromorphic types of architectures. I think you'll start to see some benefits. It might not be in the data centers because that's such a huge market. You need like billions of products to work well, but it could be in some niche applications first, like for the cheaper products like maybe your cell phone or some appliances, um, just to lower the energy consumption. And once you develop a market and you grow that market, then you can actually broaden the number of the range of applications. So there's this concept called disruptive innovation, where you can actually you have to start with some niche market where you have a real competitive advantage, even though you might not be the most cost effective. But as long as you find a niche in the market and to fund further development of that technology, then eventually you can become the dominant technology. So I think this is kind of what we're aiming for, is to facilitate more disruptive innovations to come to market to bridge that gap between research and high volume manufacturing.
So, my understanding of the way that the hubs operate is that there will be a collection of proposed initiatives that go through the hub, then are ultimately determined by the folks at the Pentagon on which projects should be funded and which ones shouldn't, and then the research gets done in concert with the hub.
Mm.
With that being said, what advice would you give people that are interested in working with your hub in potential new ideas, new concepts, and how would you recommend that if someone has never been engaged, what they should do, and what would the process look like?
Yeah, the first thing is to engage. So we have meetings that are open to the public, and of course, people can reach out to us via our information that's available on our website. The key is so that we get to know you, and then we can connect you with other people who might be good collaborators. Because usually these projects involve collaborations with multiple principal investigators, maybe multiple institutions, industry, and academia. So it's for the challenges we're trying to address, the solutions are just as complex, and so it requires teaming. So I think that's the biggest challenge for a newcomer, is to really get connected to our network, and we're happy to talk with people and grow our network because we really do need the best ideas to help these pretty challenging to reach our goals, which are pretty ambitious.
Yeah, it's the way I interpret that is if let's say I'm a company that's interested in putting forward a proposal, it's better to join the hub and then find teaming partners. So I'm not a, singularity or a single,
Yeah.
proposal here.
Yes.
Using the ecosystem that you guys have developed puts me in a better position than trying to do it alone. Do I have that right?
That's you put it very well, better than I could. Thank
Oh,
you.
excellent. So when I mentioned the description of the microelectronics hubs, it's a 5-year program that is funded through originally the CHIPS initiative. After the 5 years, what do you see the future of the hub looking like? How do you see the great work that is going to be comprised in those 5 years continuing on?
It's a great question. Nothing is certain, and we should not take anything for granted. But the hope is that if we show the value of the program, if we achieve our milestones and have real impact in the industry, that people in society and in the nation can recognize, then we will have shown the return on the government's investment. Hopefully, it returns more than one, right? Much more than one, so that we can have the next phase of microelectronics commons funded. But we do have to prove that our value. That's for sure. And that way, maybe in the next round, there could be some more funding provided by other sources. We could diversify the sources of funding. Perhaps industry through membership fees um, can help to fund some of the research. So it's not primarily the federal government.
And what we'll do is in the show notes, we'll put the link for people to sign up to the hub. So that way
Thank you.
it's a very easy access. So they're not searching all over the internet.
Yes.
One of the things that you were talking about value within industry and with the hub, your time has actually been very valuable. Many people want to take portions of your time, which leads to one of your more recent roles, which is with the National Academies. And I believe it's the National Academies of Engineering, correct?
Yes.
Can you describe your role there as what you're doing?
Sure. My role right now is president of the National Academy of Engineering. And the mission of the National Academy of Engineering is to advance the welfare of the United States by advising our nation's leaders on matters pertaining to engineering and technology. And it's also by supporting a vibrant engineering profession in this nation and advancing public appreciation for engineering. Because if we don't have a good, strong workforce in engineering, which is the engine of innovation, then we're not going to be able to translate scientific discovery into new devices, processes, technologies, systems that will benefit people. And the US will not be able to keep up in this technology race that we are in. So whether or not it's in cyberspace or in real space, monitoring everything that's happening on Earth at any time, it requires innovation, continued advancements in technology, and that won't be possible if we don't have a strong domestic workforce. So that's kind of the mission of the NAE, is to help ensure that the U.S. is going to have a bright future by marshaling the resources, leading engineers in this country, and not only identifying them but engaging them in our mission.
So, with the small familiarity I have with the national academies, they have sometimes a set of target areas to look into, and either talk with world experts about and
Mhm.
publish their findings on
Yes,
and recommendations on way forward.
that's right.
What are some of the key focus areas right now that you're looking at? You mentioned workforce as being one of the big
Yes,
ones.
yes.
Um,
So just to clarify, when the National Academies provides conducts reports, very rigorous through a rigorous process, including expert review, um, it's actually at the request of the government. So some leader in some office in the government or in Congress, or National Science Foundation will request a study to be performed. So that's the first thing. So we have to maintain good relationships with the nation's leaders to meet their needs. I view it as, what can we do to apply our expertise to help our leaders succeed in leading the nation to a brighter future. So that's kind of the way I view our work.
How are those that are helping to create and formulate workforce development capabilities, specifically within engineering,
Mhm.
able to either connect in with the national academies or help to showcase what they're doing? Because there's a number of different government sponsored efforts that are out there. You have some of the things that are coming out of the Office of Secretary of Defense for Research and Engineering via the SCALE program as being one example. There's others like the University of Arkansas that is putting forward kind of a learn by anywhere approach. How do you recommend their work coordinate with the national academies?
That's a great question. I realize I didn't answer your previous question. So now we're living in the era of AI. So certainly there are multiple studies looking at the impact of AI, like on the future workforce, specifically also on we're starting to look at on education. Yeah, so that those are examples of studies that the academies are undertaking. Um, in terms of coordinating workforce development efforts across the nation, I think this is where there's an opportunity for the National Academy to step up and help to coordinate activities so that if there's a wonderful program in Arkansas or in Indiana, then other regions of the nation, if they're trying to build out their local ecosystem for workforce development to meet their local industry needs, they can learn from those successful models. There's no reason why each region of the country needs to figure out how to promote collaboration between industry and academia, whether or not it's university or college or K through 12. We should propagate, share best practices, and share curricular content if that's appropriate. That way, if we help our nation as a whole, then each of us will benefit because we are part of this nation. So I think that's a role that the NAE can play in the more so in the future.
Well, it's exciting to hear your new role in overseeing the National Academies of Engineering. It's been something that has I've seen on the National Academy of Sciences influence a lot of decisions that turn into funded activities by the federal government.
That's true.
One of the big ones that I've observed was this big gap that they had in the radiation test infrastructure
Mm.
that the National Academies of Sciences clearly identified as a problem space, and based on their not only literature review, their findings and their recommendations, has put forward a number of initiatives that have spurred out, funded activities like the combined radiation effects over facility over in NSWC Crane, or
Mm.
the new proton facility that's over in Auburn. So there is an absolute ear to the stuff that you're doing, and it's exciting to hear that you're leading the charge here.
Yeah,
One of the things that you mentioned at the very beginning was the influence that your husband had in your life, especially with
early on.
yeah, when you were doing this stuff early on. Have there been any other mentors that have been kind of a guiding light in your life that have helped to either give you a perspective that helped out with all these different varying hats that you have, or in any way, shape, or form?
Sure. I think all along my life journey, I've been very fortunate to have mentors or role models, starting with my parents. My father actually was an electrical engineer in college. He changed fields to become a scientist after that. So I got to meet some of his former classmates, and they all served as nice role models for me. They're engineering professionals in Silicon Valley. And then my husband was more senior than I was in school. And then when I went to work at Xerox PARC, my manager, my colleagues, and then at the university, maybe more experienced faculty members, department chairs, deans, provosts, and even the chancellor. I've always been fortunate to work with outstanding people who naturally like to help others. And I think it's mutually rewarding, right? If you help somebody and you can see that they go on and help others, that's a big return on investment as well, right?
Absolutely.
So it's a virtuous cycle.
100%. And I mean, you've been such an influence, not only into the industry, but these varying hats that we've described today. I guess kind of the closing thoughts that I would have here, or the closing question that I would have here and it'll be either or kind of thing. So whatever one you
Okay,
feel
sure.
comfortable with. The first one would be, we're shrinking down the density of microelectronics into a spot where there's no longer the laws of physics that allow for the shrinking to happen. We're getting close to that place. Where do you see the future of innovation in hardware for microelectronics? That's one option. The other one is from a future of innovation from a government funded perspective. Where do you think that the biggest impact could be? And you can answer both if you'd like, but I'm curious to see both of those questions. Which one you feel
Hmm.
comfortable in answering?
Well, when you talk about shrinking things down on in a smaller area, fundamentally it comes down to the functionality. So how you can get more functionality out of a chip of a fixed size. So you can do so by fitting more transistors, more switches, more components on a substrate. But you also can innovate new technologies that will allow you to perform more functions per component. So that's one of the directions of my research over the past 20 years is to how do we replace the transistor with something that is more functional? Transistor just you apply a voltage and it allows current to flow or not. Can we come up with some solid state device that does more than that? That way you can actually get the same functionality with fewer components and therefore make it easier to fit to increase the functional density. So that's still an active area of research. In terms of how the government can invest in to ensure that the U.S. is a leader in innovation, I think. So now I have a biased view. I think the government can invest more in engineering, and I think this is a fundamental challenge in the United States today, as compared with some other countries in the world. Um, in a technology dependent society, we really do need to have a technologically literate public and have a strong engineering workforce because it is the engineers, whether or not they're the people who build things or and fix things or the people who innovate new devices, things that never existed. We need a strong engineering workforce. Otherwise, there's not as much value in advancing a scientific discovery because there's no impact. Maybe other countries can capitalize on the new knowledge that you've developed found in your country. But if other countries lead in commercializing that knowledge, then the US will fall further behind. And like I said, we are in a competitive environment economically and from a military standpoint as well. If we don't have the latest technologies, then we're not going to have the best um, equipment to monitor what's going on, to maintain safety, health and safety in our nation, so on and so forth. So I would say it'd be wonderful if the federal government um, funds engineering innovation and translation into manufacturing just as much as it has funded science.
That's interesting because there's a ripple effect. You fund R&D that helps to bolster a stronger workforce development capability, which provides the future for the United States to be not only influential but have a core capability that supports industry, supports all of the different nuances that electronics has. I mentioned a lot of these radiation facilities, but experts that understand how radiation bombardment interfaces with electronic components. So the work
Scientific knowledge is very foundational and important, for sure. Yeah.
So I will leave with the fact that your research in doing more than just a switching transistor has really piqued my interest. I think I
Okay.
could spend hours, just talking to you about this. It's got me thinking about the what ifs, which I think is one of the fundamental pieces of any good research. What are the possibilities and how do we drive down this path? So,
Mhm.
Tsu-Jae, it has been a pleasure
No,
speaking with
thank
you.
you, Daniel.
Thank you
It's
for
my
being here on
pleasure.
the podcast, and I look forward to seeing not only the impact that you have from a hub perspective, but from the National Academy side, and also your research that we were just talking about. So, thank you very much for the
Yeah.
time.
Thank you. My pleasure.